Welcome back. Applied Physics Lecture Series, Quantum Mechanics, Lecture 8, Particle in One-Dimensional Potential Box. In quantum mechanics, all the problems related to the motion of a micro object will be solved with help of Schrodinger's time-independent wave equation. So here, this is the case study, which is nothing but particle enclosed in a one-dimensional potential box, and how you will apply Schrodinger's wave equation to solve the problem will be discussed under this topic. So here, if you consider particle in one-dimensional potential box, that is an example for bound state. What is meant by bound state? The motion of a particle is restricted to a specific region will be called as bound state. Then in that state, if you study how the energy levels are arised, eigenvalues and eigenfunctions are arised, all those we will discuss under the category of this particle enclosed in a one-dimensional potential box problem. If you study the bound state in one dimension by using this example, so it will be applicable for all the particles present in case of any material. Because in case of any material, all the particles are restricted to the bound state. Those are strictly present within the material because of surface potential. Therefore, if you provide the solution for this problem with help of Schrodinger's wave equation, the solution will be extended to for all the remaining problems which are experiencing bound state. If one-dimensional potential box is assumed with infinitely heighted walls, and the width of the potential box will be considered as A, and the particle is placed inside the potential box, because of this infinitely heighted walls, the particle is present inside the box forever. Therefore, the probability of finding the particle inside the potential box is always 1. And we are studying the motion of such a particle inside the potential box in only one dimension. So for our convenience, that is along x direction. Therefore, here the boundary conditions for the particle which is to be moved inside the potential box are x equals to 0 and x equals to a, because here a is the width of the potential box. And during such a movement inside the potential box, if the particle is colliding with walls of the potential box, such a collisions are considered as perfectly elastic collisions. As a result, nothing will be exchanged between those two. Therefore, always, because of these infinitely heighted walls and by assuming constant potential because of that elastic collisions, the particle is always present inside the potential box. Finally, the particle which is present inside the potential box, as a result, the probability of finding the particle inside the box is always 0. Then, if you consider exactly, if one-dimensional motion of a particle is assumed to take place with zero potential energy over a fixed distance, and if the potential energy is assumed to become infinite at the extremities of this distance, and it is described as the particle in one-dimensional potential box, and it is the simplest example of all motions in a bound state. Then Schrodinger's wave equation will be applied to study the motion of such a particle in one-dimensional potential box. Sometimes this is also called as one-dimensional potential well, to show how quantum numbers, discrete values of energy and zero-point energy will arise. The box can be represented by a potential well of width A. The potential assumed to be constant and equal to 0 inside the potential box. On the walls and outside the potential is infinite, that is, potential energy becomes infinite because of infinitely heighted walls. The boundary conditions are, if v of x is equals to 0, when 0 less than x less than a, then psi of x becomes 1. In the same way, if v of x is infinite, when 0 less than x less than 0 greater than x greater than a, and psi of x becomes 0, where psi of x is probability of finding the particle inside the box. The Schrodinger's wave equation for free particle in the potential box can be written as d square psi by dx square plus 8 pi square m by h square e minus v into psi equals to 0. But v is 0 because the particle is inside the box. Hence, the equation can be written as d square psi by dx square plus 8 pi square m by h square e psi equals to 0. And here in the equation, 8 pi square m by h square into E is constant. That's why all those terms will be represented with a new constant K called as wave propagation vector. As a result, this equation becomes d square psi by dx square plus k square psi equals to 0. Then we have to provide the solution for this one. So the general solution for this equation is in the form of psi of x equals to a sin kx plus b cos kx. Applying the first boundary condition, that is, x equals to 0, in between the limits 0 less than x less than a. Therefore, a sin k0 plus b cos k0 is equals to 0. As a result, the constant b becomes 0. Then to get the value of another constant which is present in the general solution, that is a, we have to apply the second boundary condition. By applying the second boundary condition, x equals to a also, we are getting the value of psi f x is equals to 0. Hence, either a equals to 0 or sin ka equals to 0. But here we are taking sin ka as 0, because if a becomes 0, then there is no solution for the particle, but the particle is present inside the box. That's why we assume a is not equals to 0. As a result, sin ka equals to 0. Therefore, the general solution for this one is k equals to n pi implies k equals to n pi by a, where n is an integer which starts from 1 onwards. Here n is not equals to 0, because if n becomes 0, wave propagation vector k becomes 0. As a result, energy is also 0. But the particle cannot move with 0 potential energy. That's why here n equals to 0 is not allowed. Substituting the value of k in equation 5, we get E is equals to n square h square by 8m a square. This is known as expression for discrete values of energy levels in a bound state. Here A is the energy, n is the positive integer, starts from 1 onwards, h is the Planck's constant, m is the mass of the particle which is present inside the box, and a is the width of the potential box. The lowest energy of the particle is when n equals to 1. As a result, En becomes E1. Therefore, E1 is equals to h square by 8 me square is the lowest energy or ground state energy or 0 point energy of the bound system. The wave function psi of x corresponding to En is also called as eigenfunctions of the particle, and the integer n corresponding to the energy En is called as quantum number of that energy level En. Then substitute the value of b equals to 0 and k equals to n pi by a in equation 6. We will get psi of x is equals to a sin kx plus b cos kx. But b is 0. That's why sin of x is equals to a sin n pi by x into a. According to the normalization condition, we will get in the physical significance of the wave function case, the total probability of the particle in somewhere in the potential box must be equals to 1. Therefore, integral 0 to a sin of square dx is equals to 1. Substitute the value of wave function and integrate. We will get the value of a is square root of 2 by a. Therefore, the normalized wave function is sin of x is equals to square root of 2 by a sin n pi by x by a. And we will see the two diagrams where the propagation of wave function will take place in the potential box. So which is clearly gives the particle which is present in the bound state, which is having these following wave functions. Thanks for watching.